Today we are going through Physics 062543 May-June 2022 paper. Question number 1. A battery provides energy to an electric car. Part A says the electric car has an acceleration of this when it moves from rest. The combined mass of the car and its driver is 1600 kg. Part I says calculate the time taken to reach a speed of this. So we know the formula acceleration equals change in velocity divided by time. And we are supposed to find out time, so we can rearrange our formula and we get change in velocity divided by acceleration equals time. So we have the velocity of the car, which is 28 meters per second, and our initial velocity was 0, so minus 0, divided by acceleration, which is 2.9. So we get our answer as 9.655, which is approximately 9.70. So 9.70, and we can write our units also, which is seconds. Part 2 says calculate the force required to produce this acceleration. So we have the formula again, F equals ma. We have the acceleration here, and we have the mass of the car and driver, so we can just multiply them together to find our answer. So it's gonna be 1600 into 2.9 meters per second squared, which is gonna be around 4640, which we can write as 4600 Newton. Part 3 says calculate the kinetic energy of the car when its speed is 28 meters per second. So we know the formula of kinetic energy, which is half mv squared. We know the mass, which is 1600, and we know the velocity, which is 28. So we can square this and we'll get our answer as kinetic energy. So we can put this in our calculator, half mv squared, and we get our answer as 6.3 into 10 raised to the power 5. So we have our kinetic energy equals 6.3 into 10 raised to the power 5. We can write the same thing here and give our units also, which is joules. Part B says the time taken for the car battery to recharge from zero charge to full charge is this. The charge is delivered to the battery by a charger with current of this. Calculate the charge supplied by the charger. We can find out like what things are given to us. First of all, we are given with the time, which is 8.3 hours. We can convert this into seconds, which is going to be 8.3 into minutes, which is 60 minutes, and then into seconds, which is 60 seconds. So we can find out here 8.3 into 60, which is going to give us 29,880. And this is our seconds, which is time. And we are given with the current, which is I, so 32 ampere. And we are supposed to find charge, which is Q. So we have an equation which is Q equals IT, and we just have to multiply the current with time to get our charge. So we have our current, which is 32, and we have our time, which is 29880 seconds. So we can just multiply this in our calculator and we'll get our answer as 9.6 into 10 raised to the power 5. So this is 9.6 into 10 raised to the power 5. We can write the same thing here, and don't forget to add your units, which is coulomb. Part C says under ideal condition, the car can travel a maximum distance of this when the battery is fully charged. Suggests why in normal use the car needs to be recharged after traveling less than 390 kilometers. The reason is that in real situation, the acceleration of the car is not constant. So we can write down that in real situation, the acceleration might be increasing or decreasing, which will take more charge. So that's why it has to be charged before covering 390 kilometers. So we can write down here, the acceleration of the car is not constant. Therefore, it would use more energy and would have to be charged earlier. We'll get 1 mark for this. And we are done with question number 1. Question number 2. Water is held behind a dam in a hydroelectric power scheme. Part A says state the main form of energy stored in the water behind the dam. So this is pretty straightforward answer, which is gravitational potential energy. You can write this in full form or short form. You'll get 1 mark for this. Part B says the water is released from the dam and falls a vertical height of this at a rate of this. So part I says calculate the rate at which energy is transferred by the falling water. The most important thing to know about this question is rate is equal to power, and our power is energy divided by time. And the form of energy we are using here is gravitational potential energy. So we can find out our GPE, which is going to be mgh. We have our mass, which is 480, into our gravitational constant, which is 10, into our height, which is 410, which is going to give us our answer as 480 into 10 into 410, 1.97 into 10 raised to power 6. We found out our energy, and we just divide this by time, which is going to be 1 second. So we get our rate, which is 1.97 into 10 raised to power 6. We can write down our answer here, 1.97 into 10 raised to power 6. Part 2 says the power scheme supplies current of this at a voltage of this. Calculate the efficiency of the power scheme. How do we calculate efficiency? The formula for efficiency is useful output divided by total into 100. So for finding useful power, what we have to do is use the formula V equals IV, because we are given with current and we are given with voltage. So we can find out our useful power, which is going to be 270 into 6000, which is going to give us our answer as 1.6 into 10 raised to power 6. We found out our useful power. We have our total power, which we calculated in the first part, and we can just divide both of these and multiply with 100. So our useful, which is 1.6 into 10 raised to power 6, divided by 1.97 into 10 raised to power 6 into 100, which is going to give us our answer as 1.6 into 10 raised to power 6, 82 percentage. So it's going to be approximately 82 percentage. Part C says hydroelectric energy is a renewable form of energy. The sub question, it says state one disadvantage of hydroelectric power scheme. So the disadvantage of using a dam is that if the dam breaks, there will be flood. So we can write our risk here. Risk of flood if the dam breaks. And part 2 says state one other renewable source of energy. So we have geothermal energy, we have wind, we have tidal, we can write anything here. So for this part, I will write tidal and wind. So we'll get 1 mark for this. And we are done with question number 2. Question number 3. Part A says figure 3.1 shows a boat stored in a shed. The boat is suspended from the ceiling of the shed by 2 ropes. This is the ceiling. We have 2 ropes. There are tension in both of them, and there's a boat here. The tension T in each of the ropes is 75 newtons. And part I says draw a vector diagram to determine the resultant force exerted by the 2 ropes on the boat. State the scale you used. So for this question, we're going to use the scale as 10 Newton equals 1 centimeter. And we're going to draw the same diagram, which is here. So as we can see here in the question, it says that tension in these rope is 7.5, which is 75 Newton. So we can just write here 7.5, 7.5, as we are taking 10 Newton as 1 centimeter. So this is going to be 7.5 as well. If you do the math, you'll know that this is also 7.5. So we can draw the same diagram down, and we'll continue next. So here you can see I have drawn vector diagram here. This is 7.5 centimeter, this is 7.5 centimeter, and this is 60 degrees. This is also 60 degrees, and we have this as 7.5 centimeter as well. Now what we have to do is the same drawing we have to reflect on this side. So what do we have to do for that is do the same thing, measure 60 degrees from this side and measure 60 degrees from left side as well, and draw our resultant force on this side for the same diagram. I'll represent the resultant force as orange. It's going to be like this. And these are our resultant forces. Now to find the main magnitude of resultant force, what we have to do is find out this distance. Now to find out this distance, we have to use scale. What we can do here is we can write here 7.5 centimeter and 7.5 centimeter. So it's now when we use our scale, we can see that this is approximately 13 centimeter. This whole thing is 13 centimeter. And we know that 10 Newton equals 1 centimeter. So we can multiply 13 into 10, which is going to give us 130 Newton. So this is going to be our resultant force. And our direction of the resultant force is going to be upwards because the tension is upward both sides. So this is going to be upward as well. So we can go down and fill our answers here. So magnitude of resultant force is going to be 130 Newton, and the direction of the force is going to be upward north. And we'll get 4 mark for this, 3 mark for these, and 1 mark for diagram. Part 2 says determine the mass of the boat. So how do we find mass? We have the formula F equals ma. We just found out the resultant force. So we have the force as 130 Newton as our force. And to find out our mass, we can just rearrange our formula, which is going to be F divided by A, which is equals to mass. And acceleration, we know the gravitational constant is 10. So 130 divided by 10 is going to give us our answer as 13. And our answer for this question is going to be 13 kilograms. Part B says force is a vector. Circle around 2 other quantities in the list which are vectors. So acceleration we know is a vector. Density is not a vector, it's a quantity. Energy is not a vector because energy equals power into time. And mass is not a vector. Momentum is a vector because momentum equals mv, mass into velocity, and velocity is a vector, so momentum also becomes vector. Power is not a vector because power equals energy divided by time, and refractive index is also not a vector. So these two are the only things which are vector in this list. And we are done with question number 3. Question number 4. Part A says figure 4.1 shows a apparatus used to observe the motion of smoke particles, which is Brownian motion. The glass cell has light shining on it from the side. The smoke particles are seen as bright specks of light when looking through the microscope. Part I says draw the path of one of the brightest specks of light. So what we have to do here is just draw a smoke particle because they have told us that smoke particles are seen as bright specks. So we have to draw a smoke particle. Let's suppose this is considered as smoke particle and maybe this is considered as air molecule. So path of the smoke particle is gonna be random wherever the air molecule hits the smoke particle. It's gonna be random. Might be here, it might be here. It depends on how the air molecule hits the smoke particle, and we'll get 2 marks for this. Part 2 says explain in terms of forces and motion of air molecule the cause of motion of the smoke particles. So first of all, we have to read the question properly. It says in terms of forces and motion of air molecules. Now for example, we have air molecule here. This air molecule has high momentum and it's moving with high velocity. So what happens is, let's suppose we have a smoke particle sitting here which is initially at rest, and what might happen is this air molecule might go and hit the smoke particle, might collide with it, and depending on the direction from where air molecule will hit the smoke particle, that would determine the direction where the smoke particle will go. For example, in this case, it might go on this side, or if it hits like straight, it might go on this side here. It all depends on how the air molecule hits the smoke particle. So in simple words, we can explain this. Air molecules are moving in random directions. And then what happens is they move faster than smoke particles as their size is relatively small. So they have more momentum. Their size is relatively small. Now what happens is this air molecule will go and collide with the smoke particle. Here we can see here in this illustration as well. So we can write down here air molecule collide with smoke particle, applying force on it. And this part is essentially for covering this part of the question, which is in terms of forces. So we have to mention anything related to force as well to get all 4 marks. And for the last part, we can write as thus the smoke particle moves in random motion. And we'll get 4 marks for this. First mark for the first statement, second mark for the second statement, and third mark for the third statement. And don't forget to mention anything related to force because you might lose mark for that. And fourth mark for the last statement. Part B says the temperature of the air in a sealed gas container is increased. Part I says explain in terms of molecules why the internal energy of the air increases. So as we know, temperature is directly proportional to kinetic energy. As you increase the temperature, kinetic energy increases. As you decrease the temperature, the kinetic energy will also decrease. And we have the formula of kinetic energy, which is half mv square. As we increase the kinetic energy, velocity of the molecules will also increase. And that's the reason why the internal energy of the air increases inside. So we can write down here as temperature increases, the kinetic energy of the molecule also increases. And we'll get 1 mark for this. Part 2 says explain in terms of molecules why the pressure of the air also increases. Now we have the formula for pressure, which is pressure equals force divided by area. And we know that force is change in momentum divided by change in time. Momentum is shown as p. And from this equation we can see that momentum is directly proportional to force. What is momentum? Momentum is mass into velocity. If we see the kinetic energy formula here, we can see the velocity increases as you increase the kinetic energy. So as you increase the kinetic energy, the momentum increases, therefore force increases. Since force increases, the pressure also increases. So we can write down here that as the momentum increases, pressure increases. And we can mention our equations here, which are gonna be pressure is directly proportional to force and force is directly proportional to change in momentum. We'll get 2 marks for this. And we are done with question number 4. Question number 5. Part A says define specific heat capacity. We know what specific heat capacity is. It is energy required to raise a temperature of unit mass by 1 degree Celsius. So we can write down here and we'll get 2 marks for this. First mark is going to be for increase in temperature per unit mass, and the second is going to be for 1 degree Celsius. Part B says a bowl contains 500 centimeter cube of water at temperature of this. The bowl of water is placed in a freezer for several hours. When the bowl is removed from the freezer, it contains ice at temperature of this. The density of the water is this. Part I says calculate the mass of the water in the bowl when it's placed in the freezer. So we know that density equals mass divided by volume, and we are supposed to find mass, so we can rearrange our formula to find m, which is gonna be P into V. We have P, which is density, which is 1000 kg per meter cube, and into V, which is gonna be our volume here. And note that this is in centimeter cube. This volume is in centimeter cube, so we have to convert this into meter cube. So how do we convert this into meter cube? We multiply this by 10 raised to the power minus 2 and then cube this to convert this into meter cube. So we take out our calculator, which is going to give us our answer for this part, and it's going to be 5 into 10 raised to the power minus 4. So we can multiply this here, 5 into 10 raised to the power minus 4, and we get our answer for mass here. Just multiply this by 1000 and we'll get our answer as 0.50 kg. So we can write here 0.50 kg, and we'll get 2 marks for this. Part 2 says the specific heat capacity of water is this, the specific heat capacity of ice is this, the specific latent heat of fusion of water is this. Calculate the energy given out as the water cools from 5 degrees Celsius to ice at minus 18 degrees Celsius. So this part is really tricky. We have 3 stages here. First is where the temperature is 5 degrees Celsius. Second is where the temperature is 0 degrees Celsius. And third, where the temperature is minus 18 degrees Celsius. We have 3 parts because it's kept in the freezer when it's water. So here it's water, here it changes to ice, and here it stays as ice, but then the temperature decreases to minus 18. So we have 3 steps here. And for this question, we have to find energy for all 3 of them. So for finding for all 3 of them, we have 2 equations for finding energy. E equals mc delta T, E equals ml. And the first equation is going to be used for these 2 scenarios, as there is temperature difference. And for the second equation, we're going to use the middle one. So first what we have to do is find out the energy of the water. So E equals m. We found out the mass, which is 0.50. C, which is the capacity. We're given with capacity of water here, which is 4200. So 4200 into delta T, which is temperature change, which is 5 degrees Celsius. So we can multiply this and write it here. It's going to be 0.50 into 4200 into 5, which is going to be 10,500. And this is going to be our energy for water. The second part we're going to use is E equal ml. So we have our mass as 0.50, and latent heat of fusion is given here in the question, which is 3.3 into 10 raised to the power 5. So we can write down here 3.3 into 10 raised to the power 5. And we'll find out this, which is going to be 0.50 into 3.3 into 10 raised to the power 5, which is going to be 165,000. And the last one we're going to find is for this one, and we're going to use the first equation again, which is E equals mc delta T. Now in this case we have 0.50 and C capacity is 2100, and our delta T is going to be 18. So we can calculate this 0.50 into 2100 into 18, which is going to give us our answer as 18,900. And we just have to add all of these. So we can use a calculator for that. 10500 plus 165000 plus 18900, and we get our answer as 1.9 into 10 raised to power 5. We can write the same thing here. We add them, we get 194400, which is also known as 1.9 into 10 raised to power 5. So we can write the same thing here, 1.9 into 10 raised to power 5 joules. And we are done with question number 5. Question number 6. Part A, I says figure 6.1 shows a crust of plain water wave approaching a barrier with a gap. This is the crust and this is the barrier here. On figure 6.1, draw 3 crust of the water wave to right of the barrier. So what we can do here is draw 2 lines with the 90-degree angle in between. So here we have 2 lines which have 90-degree angle, and then what we can do is just measure how much the size is. It's around this much, so we can add space in between like this, and here we can draw the crust. And it's going to be like this. They told us to draw only 3 crust, so we are only gonna draw 3 crust, and we could probably erase these lines, and it's gonna be like this. So we'll get 2 marks for this. Part 2 says figure 6.2 shows crust of a plain water wave in deep water approaching a region of shallow water. So we can see the direction of the water here, and this is the boundary, this is deep water and this is shallow water. The water wave moves more slowly in shallow water. On figure 6.2, draw 3 crust of the water wave in the shallow water and show the direction of the travel of the wave in the shallow water. So it is saying here that it moves more slowly in shallow water. So the crust are gonna move away from the normal. So we can see here our normal is gonna be here at 90-degree angle. Here normal, here normal as well. So this is gonna move away from the normal. So it's gonna be like this and like this. And there's gonna be one more wave because we have to show 3 crust. So for the third crust, what we are gonna do is draw a blue line here with same distance, and we can show it like this, the small black, indicating that this was the previous crust in the deep water. And for showing the direction, what we can do is we can just put an arrow here which is showing for the deep water, and for shallow water it's gonna be a little bit bent here on this side. It's gonna be like this, and we'll get 2 marks for drawing 3 crust and 1 mark for drawing the arrow. Part B says state 2 ways in which transverse waves differ from longitudinal waves. So transverse waves are like this, and we know that the energy travels like this on this side, and it is perpendicular to the wavefront. So we can write down here the direction of travel is perpendicular to the wavefront. And as we can see in the diagram, this has crust and trough as well. So we can write here that transverse waves have crust and trough. And we'll get 2 marks for this. Part C, I says state a typical value of speed of sound in the water. If you Google this up, you will get like all the speeds in different mediums. You have to learn for air and other substances, like common things. So you can Google it up. I'll show it on the side as well. So it's approximately 1500. Part 2 says explain why sound travels faster in the water than in air. So the reason is that sound travels faster in denser medium. So we can write down here. And we are done with question number 6. Question number 7. Part A says figure 7.1 shows a plain view of a room there's a plane mirror on one wall and a picture across the whole of the wall AB. A person is standing at point X and is looking at the mirror. The person cannot see all of the picture on wall AB reflected in the mirror. There's a point P on wall AB, which is closest to point A, that the person can see reflected in the mirror. So we have to note here that the point P is closer to point A. So for drawing, it says on figure 7.1, draw a reflected ray and incident ray to show the position of point P. So what we can do is here, we can draw our point P somewhere here, closest to A, and we can reflect this ray. Let's suppose this is the incident ray which goes and hits with the mirror, and we call it as incident ray. And there's another ray which is reflected ray, which is gonna go till point X like this, and we can show the direction of the ray by putting arrows. So this is gonna be our incident ray, and this is gonna be our reflected ray. Part B says state two properties of the image formed by the mirror. So as we know, mirrors form inverted images, so it's a virtual image. And the second is that it's the same size, it's not enlarged, it's not magnified, so it's going to be the same size, and we'll get 2 marks for this. Part C says visible light is an electromagnetic wave. State the name of one region of electromagnetic spectrum in which the waves have shorter wavelengths than visible light and longer wavelengths than visible light. So for this one, we have a mnemonic here, which is Randy, Mandy in velvet uniform, extremely good looking. And as we go down from here, the wavelength gets shorter, and as we go on this side, the wavelength gets longer. So we're talking about visible light here. And for the part 1, we can either write ultraviolet, X-ray or gamma ray. So I'm just gonna write gamma ray. And for the second part, for longer wavelengths, we can write as maybe infrared or microwave or radio wave. So I can write here radio wave for this part. And we are done with question number 7. Question number 8. Part A says figure 8.1 shows a circuit. Here we have our batteries. This is light dependent resistor and this is just a normal resistor. Part I says state the name of component X. So our component X is LDR, which is light dependent resistor, and we'll get 1 mark for this. Part 2 says the potential difference across component Y is measured with a voltmeter. On figure 8.1, draw the symbol of the voltmeter and its connections to the circuit. So this is across component Y. So we're just going to draw a voltmeter here with 2 wires connected. It's going to be like this, and our voltmeter is completed. Part 3 says the electromotive force of battery is 12 voltage. Component Y has a resistance of this. In a brightly lit room, the resistance of component X is 350 ohms. So we can write down here whatever information we are given with. So we have EMF of 12 volt. We have resistance for LDR is 350 and resistance for component Y is 400. First part says calculate the current in the circuit. For calculating the current in the circuit, we need total EMF and total resistance. Only then we are gonna get our current. So we have our formula V equals IR. We have V, which is 12, divided by R is gonna give us I, which is current. So we just have to find total resistance. And as we know, resistance in series is gonna just add up. So it's gonna be 400 plus 350, which is gonna be 750. So 12 divided by 750 is gonna give us our answer as 0.016, and this is gonna be ampere. Part 2 says calculate the PD across component Y. So component Y has resistance of 400, and we have the formula V equals IR. The current is, as we calculated in the first part, 0.016. So 0.016 into R, which is 400, which is gonna give us our answer as 6.4. So our PD is gonna be 6.4 voltage. Part 4 says, in a dark room, the resistance of component X is very large. State the effect this will have on PD across component Y. So as we know, potential difference is divided by ratio. And as we know, if it's dark, the light dependent variable resistor will have more resistance. For example, this is going to have 500 if the room is dark. Then what will happen is this will take most PD and this will get less PD, because the component which has more resistance will get more PD, potential difference. So we can write down here PD potential difference in component Y decreases. And part B says suggest a practical use of component X. Component X is LDR, which is light dependent variable. This can be used for security lights at night and for security purposes. So we can write down here used for security lights at night. And we are done with question number 8. Question number 9. Part A says figure 9.1 shows a magnet on the end of a spring and coil of wire connected to a sensitive center zero galvanometer. The magnet can move freely through the coil. You can see the magnet here. And this is center zero galvanometer, and these are the springs. So part I says the magnet is pulled down and released. Describe and explain what happens to the needle of the sensitive galvanometer. So here I'm showing you an illustration of what the question is basically trying to explain you. It's not an exact accurate representation, but you can get the idea out of this. So when I'm trying to move the magnet here, you can see the galvanometer is showing some changes in the needle, left to right and all. And as I slow down, the galvanometer needle moves slowly as well. And if I show you the fields, you can see the magnetic field are cutting the coil, and only then at that point the galvanometer is moving. What is essentially happening is the magnetic field and current are perpendicular, and as the coil cuts the magnetic field, an EMF is produced, and the induced EMF is like trying to oppose the force causing it. Like you're literally pushing the magnet inside the coil, and there's a force acting on it to oppose that motion. So that's why the needle is oscillating left to right. So we can basically write the same thing here in our question paper. We'll go back to our question paper here. So we can write here magnetic field and current are perpendicular. Second part is that as the coil cuts the magnetic field, an EMF is produced. Hence what happens is the induced EMF is trying to oppose the force causing it. The last part we can say is that the needle oscillates left to right. And we'll get 4 marks for this. The marks distribution is going to be simple: first, second, third, and fourth. Make sure to clear this concept because sometimes they ask you like weird type of questions for this. And basically this law is known as Lenz's law. You can watch some YouTube videos on this as well. Part 2 says the magnet is replaced with a stronger magnet. State the effect of using a stronger magnet on what happens to the needle of the galvanometer. So what will happen is as you use a stronger magnet, there will be more deflection. and you'll get 1 mark for this. Part B says a step-up transformer is used to step up the output voltage of a power station from this to this for transmission along power lines. The number of turns on secondary coil is this. Calculate the number of turns in the primary coil. So we have the formula here, NP, which means number of primary coil, divided by VP equals NS divided by VS. So we're given with number of turns in secondary coil, which is 36,000, divided by the potential difference given, which is 400,000. And we can move this VP here to find out NP, which is going to multiply here in this side, which is going to be 25,000. And we'll get our answer for NP. So we can find this out from our calculator, which is going to be 36,000 divided by 400,000 into 25,000. And this will give us our answer as 2250. We can round this off to 2,300. And we are done with question number 9. Question number 10. A student places a sample of an isotope of this Pa234 near a radiation detector. The reading on the detector taken every 20 seconds are recorded in the table 10.1. You can see the table here. Figure 10.1 shows a graph of count rate due to the sample against time. You can see the graph here. Part A says explain why the reading in table 10.1 are not the same as those plotted on the graph. So the reason why this is not same as the graph, because you can see here the count rate at the beginning in the table is 101 and count rate in the beginning at the graph is 80. So there must be a background radiation in the table. So this has background radiation and this doesn't have background radiation. And we can explain and write it here as well. Background radiation present in the table and background radiation is removed in the graph. And we'll get 2 marks for this. First mark is going to be for stating that the background radiation is present in the table, and second mark that the background radiation is removed from the graph. Part B says using the graph in figure 10.1 determine the half-life of the isotope Pa. So we can see here that the total number of count rate is 80 is equal to 80 in the graph, and for determining the half-life, if you divide this by 2, it should be 40. The count rate should be 40. So we can go up to the graph and find the count rate here and take our time out from the graph. So you can see here our time is approximately 72, and that is because one box represents 4 here. So we can write down here that the half-life is 72. Part C says the nuclear notation for isotope is this, and Pa decays to an isotope of uranium by beta emission. Write down the nuclear notation for this decay of Pa. So first what we can do is we can write down our letters. So we have Pa on the left side, which decays to U plus beta emission, and we know that the mass number of beta is 0, so we can write down 0 here, and our atomic number is -1, so we write -1 here, and we're given with the mass number and atomic number of Pa, so we can write down same here, 234 and 91. Now we just have to use our math here. So 234 plus 0 is going to be 234, and 91 minus 1 is going to be 91 minus 1 is going to be 90. So we can write down 90 here, and we'll get 3 marks for this. This was the last question for this paper. If you have any questions, you can comment down below. I'll try to respond as soon as possible. Till then, see you in the next video. Thank you for watching. Bye bye.